When we study systems theory, the first things we need to get clear in our mind are some fundamental concepts. First is the definition of a system. It is a cohesive group of interrelated and interconnected components that work together in order to reach a certain objective. So, in order to study the behavior of the system, we study the sum of its components. Sometimes, though, a system is more than the sum of its parts, which happens when it presents emergent behaviors. And when a system presents emergent behaviors, we call it a complex system. Then there is the definition of a dynamic system, in which at least one component evolves through time and has a relation of cause and effect with the other components. The way we study systems scientifically is through mathematical models that we build based on the physical knowledge that we have on the system or based on analysis of empirical data gathered through controlled data collection. These mathematical models are fundamentally equations that are formulated on the basis of hypotheses and thus are very often almost always approximations of the system or parts of the system that we are interested in. It is impossible to avoid noise in the models because there could be some input data that simply we cannot measure, or sometimes there is any kind of non-linearity that we consider to ignore. To better understand these definitions, we can consider a couple of examples. For example, we can consider a car on the road, and here we define, based on the scope of the study, that we are performing the environment and the system. If I want to study the dynamics of the car, then I can say that the car and its components form the system. Everything outside the car is its environment, the road, the air, etc. So in this context, we consider a car on a plane with some inputs. We have some command inputs like the pedals, the acceleration, the brake, the clutch, or for example, the gear position. Then we have some outputs, position of the car in space and its velocity. Some additional parameters could be considered the quantity of the fuel, the brake consumption, etc. These parameters we can consider constant for a short period of time. Then there is another parameter that is the direction and the intensity of the wind. These last two parameters are not controllable parameters. For this, now we come at the definition of two types of input: controllable inputs that we consider as decisional variables, and we have disturbance inputs. For example, in the case of the car, the wind is a variable input that introduces in the system a probabilistic component, making the model stochastic instead of deterministic, for example. Now, for defining systems, we have mathematical models of various types. We have time domain models, so we have continuous models and discrete models. And for the discrete models, we have event-driven systems or hybrid models. We have event-based models where system changes happen through actions or occurrences that happen chronologically. And for hybrid models, we consider models that contain continuous and discrete parts. Then we have linear and nonlinear models.